Hello and welcome. In this video, I'll be covering section 7.5, which is over solving trigonometric equations. My goal for you by the end of the video is to be able to solve these trigonometric equations, whether it be a finite set of solutions or even an infinite set of solutions. So let's go ahead and start off by talking about what a trigonometric equation is. Since the word equation's involved, I hope it's not too big of a stretch to know that that means we're going to see some equal signs. And if it contains a trigonometric expression, such as sine, cosine, tangent, secant, cosecant, or cotangent, or even a combination of some of those trigonometric expressions, that would then collectively altogether be what we consider a trigonometric equation. So what we're going to be doing in this main section is actually trying to solve for specific variables, such as an x or a theta or an alpha or a beta, whatever the letter might be inside of the trigonometric function, and actually try and figure out what values would make that specific equation true. Now, some of the ones that we've encountered recently, we've actually been calling identities, meaning that they work for all numbers, not just specific values. So again, this is going to be more, how do I solve for specific situations, not so much the full generic and creating identities that we had already been dealing with in prior sections. So with all that now being said and presented, let's go ahead and jump into our first example. So when it comes to solving equations, if we think back to some of the basics of what we've done in the past, ultimately our goal is going to be, let's try and get something that makes the statement that we're starting with true. And usually, if you think back to other examples as well, you would just try and get something by itself, such as an x equals or a y equals or whatever the variable might have been. Here, what is a slightly different approach initially is, instead of me going straight towards like the goal of let's get x by itself, let's just start with how can I get the trig part by itself. So for this example, notice the trig that we have is the cosine of x. So what I would want to do is start taking anything that's not inside of the cosine and try and find a way to move it over to the other side. So the first thing that I'm able to move in this scenario would be the 1, and to cancel the 1 I would just subtract 1 from both sides, and that now gives me a new expression of 2 cosine of x equaling -1. Similar to what we would do in any other algebra problem, I would now go after any numbers that are attached but still technically outside of the function. Here it was the 2, I could then just divide over, and that now gives me cosine of x is equivalent to a -1/2. So now, since this is a ratio we should hopefully recognize from the unit circle, what I would now do is think in terms of what do I know about the unit circle and where would that ratio exist. So since cosine is the x value, ultimately what I would do is try and figure out where is the x value equal to -1/2. So that should be over here in the second and third quadrants, or on the left side of my unit circle. And if we think about where -1/2 would be for an x value, well, that should actually stay closer to the y-axis, so it should be the two angles that have thirds as the denominator. In the second quadrant, that actually happens to be 2 pi thirds. And in the third quadrant, it happens to be 4 pi thirds. So my two solutions for this specific problem, at least inside of the restriction it gave, which originally, notice it did say go 0 to 2 pi, so that's basically just go one time around the unit circle, identify any angles that give us that ratio, and write them down. In this case, those were the only two I would encounter, so those are the two solutions. Now, if I wanted to check my answer, first off, I would need to make sure that my calculator would be in radians, since my two answers here are in radians. And I would ultimately just figure out what is the cosine of each of those and see if it actually matches the ratio I said, which in this case was -1/2. And in fact, if I did type those two into the calculator in in radian mode, I would relatively quick see that both of them do give me a -0.5 on the screen. So I'd be happy with these two answers and be able to move on. Alright, so let's go ahead and jump into another example. In this case, not a whole lot's going to be different about our approach. We still will want to try and isolate the trig. So in this case, the trig that I have is a little bit different. It's got tangent instead of cosine. But the other thing that's also different, as you can see, is there's a 2x on the inside instead of just a single x. Ultimately, what we're going to do in that scenario is either try and take advantage of maybe one of the identities that we could use. We could technically bring a double angle formula for tangent into the problem to turn it into a single x. Honestly, in this case, it actually makes things worse, not so much better. So I'm actually going to mention, like, if you can just get the trig by itself, and that's something that we can accomplish with this one, because we can relatively easy divide the 3 over like so, and get tangent of 2x is equivalent to -3 divided by 3 would give me a -1. And now I can actually go after the tangent by just thinking on the unit circle, where is the tangent equal to -1? Well, it happens to be, if you think of tangent being slope, it should be the two angles that go through the middle of the second and third quadrants, which happen to be 3 pi fourths and 7 pi fourths. However, because of that 2 that I have in front, what I actually need to account for is I actually need to go a little bit further around. So if we think back to the first example, I went from getting rid of the tangent, it went straight to being just an x equals. We'll see this time it has 2x. So when I do the reference to the unit circle, it's actually going to be 2x equals the list of numbers. So I'm going to go ahead and just write the first couple down. 3 pi fourths, the next one I said was 7 pi fourths in the fourth quadrant. But if we think ahead, the next step would be divide the 2 off the x to get it by itself. That actually is going to bring some potentially bigger angles if I continued listing these out. If I went all the way around plus the 3 pi fourths, in other words, if I just added 2 pi to that answer, which really 2 pi in this case I can picture like it's 8 pi fourths, that gets me the next number in the list. So even though this right now initially, the 11 pi fourths that I just created is above the 2 pi, when I do the divide by 2 step next, that actually will bring it back inside of the 0 to 2 pi. So that's why generally a good rule of thumb is whatever number is in front of x is how many times I'm going to need to go around the unit circle and list out all of the answers that I encounter as I go, because when I divide by that number, it's going to take some numbers that are fairly large and potentially bring it back inside of the 0 to 2 pi range that I'm allowed to have my answers be. So since I was able to do that add 2 pi step to the 3 pi fourths, notice I can do the same thing with the 7 pi fourths and get the next one in the sequence. So again, picturing 2 pi as if it was an 8 pi fourths, I'll actually just write it as 8 pi fourths, that way I have the common denominator already, which would give me 15 pi fourths as the next angle in the list. And I could technically continue on and on and on, just keep adding 2 pi to kind of every other one of these, and it should just continue growing and growing and growing. And hopefully that process of why this continues on and on and on and on makes sense, because after all, a graph for any of these functions, in this case it's actually a tangent function, remember it just keeps repeating, it keeps repeating and keeps repeating every period that it is. And so ultimately all I'm doing is just writing all the places where that value of -1 would happen. So it would be kind of like these spots on each one of those grids, but it would just continue going forever and ever and ever, both to the left and to the right. So that's where things can get a little tricky with trig, because their graphs are repetitive. I actually have infinitely long lists of numbers unless I provide a restriction like this problem has from 0 to 2 pi. So anyway, I hope that makes sense as far as like why I now have 4 angles listed down. I could continue adding more and more and more to this list. But again, as mentioned before, to actually isolate x, I have the extra step here of I'm going to divide every single one of these by 2. And notice that takes what would be larger than 2 pi and actually brings it back inside. So if I cancel those two, now my list of x's is going to be half of 3 pi fourths. So if you think in terms of dividing by 2, what is that the same as? Well, it's the same as multiplying by a half. So really it's just going to make all of the 4's on the bottom turn into 8's. 3 pi eighths is our first solution, 7 pi eighths is the next one. Notice right now if I had stopped my list here, I haven't even made it to pi yet. 7 pi eighths, right, would be a little bit less than pi, because 8 pi eighths is actually pi. So I'm still a little bit less. So technically I hope at this point, recognize there's probably going to be some more if I have to go all the way to 2 pi. Well, that's where the next couple, right, by going that extra rotation around, when I do the divide by 2, now that brought it back inside, because after all, 2 pi really in this case would be like 16 pi eighths. Well, 11 pi eighths still is below that, so technically that needs to be a solution inside of this 0 to 2 pi range. And the very last one, I think you can probably figure it out. But again, each time the 4's on the bottom are just getting multiplied by a 2, so they are all turning into 8's. If I continued on and had the next list, let's see, that would have been, what, 8 pi more than 11 pi on top, so that would have been 19 pi fourths. If I cut that in half, it would become 19 pi eighths. That actually is too big for the 2 pi. So notice this is, in fact, the last number that fits inside of the 0 to 2 pi range for this specific problem. So again, kind of big key takeaway from this one. Not only one, let's get the trig by itself like the last problem, but this time because of the 2x that was inside, I just needed to go an extra rotation around and list those angles as well, because eventually I was going to divide them back inside of the range from 0 to 2 pi. So Again, if that would have been like a 5x, I would have had to go 5 rotations beyond whatever my first one was, and ultimately each time I do a rotation, it's just add 2 pi to whatever the first couple of numbers that I did inside of my first rotation would be. So like here, it was the adding 8 pi fourths to come up with the next sequence, and I could have technically just done all of the ones that were starting with 3 pi fourths and just added 8 repeatedly or repetitively on top to come up with that list. So the next one would have been 19 pi fourths. After that, it would have been 27 pi fourths, then 35 pi fourths. Just keep adding 8 on top and keeping the pi fourths part attached to it. Similarly, we could do the same thing starting with the 7 pi fourths, since that was the other one in the fourth quadrant, and just keep adding rotations to it. So add 8, I get 15. Add 8 again, I'd have 23 pi fourths. Add 8 again, I'd have 31 pi fourths, and so on and so forth. So once you do a couple of examples where you have to do that adding 2 pi, it becomes a little bit easier. It's probably a little confusing at first here, but the idea, I hope, is still making sense, because after all, if we go all the way around, technically the ratio is the same. It's just now the angle is slightly larger. And this kind of idea of actually having infinitely many solutions is going to come up here in the next couple of examples, or at least a few more examples that are in this video. So hopefully, if it still seems a little bit cloudy, hopefully the next couple of examples will help solidify that concept. So like I just mentioned, the first 2 examples there did have a finite set of solutions that actually fit whatever the restriction of the problem was. Both of them happen to be 0 to 2 pi, but on occasion they may have them presented in degree format, so it might say like 0 to 360 degrees. And in either of those cases, just make sure that you're answering the angles, or answering with angles that match the type of unit that you should be measuring the angle with, whether it's degrees or radians. Now, not every problem is going to have those restrictions like 0 to 360 or 0 to 2 pi. In fact, there are going to be some where it just says find all solutions. So what we end up doing in that scenario is we just go one time around. In radian format, it would just be go one time around 0 to 2 pi, and then basically write down each number. So like in the last example, it was a 3 pi fourths and a 7 pi fourths. And if you think of what we did to come up with the next 2, we just added 2 pi. So what we actually do to create an infinitely long list is we just say, well, let's just, instead of actually figuring out what the next angle is 2 pi later, let's just say, let's have an expression with it. So for that last one, it would have been like 3 pi fourths, but then plus 2 pi k to represent if I rotate any direction in a positive way or in a negative way, hence why it's saying that k is just some integer. So if I plugged in 1, technically that would give me the first rotation after 3 pi fourths. If I plug in a 2, it would be 2 rotations later, or a 3, and so on and so forth. Now if I plug in negative numbers like -4, that would be what would have been 4 rotations before 3 pi fourths. And technically all of them still would have the same spot in that second quadrant, because again, I'm going all of the way around by saying let's just do some multiple of 2 pi that I either add or subtract depending on if k is positive or negative. So that would be half of my solution, since that was the first angle that I had. The second half would be all of the ones that start at 7 pi fourths, so in the fourth quadrant, and again go all the way around in either direction, clockwise or counterclockwise, and I just say plus 2 pi k at the end of that one as well. So now notice our answer technically is by saying, as long as I pick some k value that's an integer, technically multiplying it or plugging that into this expression, it's just going to give me something that either is in the middle of the second quadrant from the first one here, or it's going to be in the middle of the fourth quadrant from my second one here. Now again, we could also do this in degrees. We could have said that this was the same as, like, what would that be, 135 degrees plus 360k, and then what would that be, 315 degrees plus 360k. We can also do it that way. It's just, again, instead of saying 2 pi, we would use 360, which I hope that's not too big of a stretch, that 2 pi and 360 are the same. I just need to make sure that whatever I'm talking about, my angle initially, I just match whatever I would be adding as a full rotation to be the same unit. So radians use 2 pi and degrees use 360. Hopefully that's no surprise. So to kind of give you an example of this idea, notice this one doesn't provide anything extra. It doesn't say only answers between these two numbers. This is just saying, hey, solve it. So if you don't see any sort of restriction, that basically means our approach in the end should be, I need to actually come up with every solution, not just a couple. So our goal still is the same as before. I want to try and get the trig all by itself first. So first I would go after the 4 that's attached to it, move it off. So divide the 4 over. I now have sine squared of x is equal to the 1/4. Next logical thing I feel like we need to do is try and get the power off of the sign. So I could take a square root at this point. Just remember, when you introduce square roots, plus or minus symbols need to go with it. I don't need it on the left side because that radical actually is going to cancel with the power, leaving me the sine of x, which is the whole point of how I want to start these. But now I need to try and simplify that fraction. So I do keep the plus or minus symbol. Square root of 1 in the numerator stays 1. Square root of 4 in the denominator actually is nice. That turns into a 2. So ultimately this time I need to figure out what are all the solutions where my sine value, which on the unit circle is the y value, happens to be either a positive 1/2, so that would be in the first and second quadrants, the ones that are closer to the x-axis, or potentially negative 1/2, which would be the ones in the third and fourth quadrant. And if you think of all of the angles that are close to the x-axis, those all should be my pi/6. Ultimately, all I would need to do is basically list out all of those one at a time, but because this is all solutions, right, this didn't restrict it, this is all solutions, that then is my key indicator of, well, each one that I write down, I'm just going to put plus 2 pi k after it, because every full rotation around, whether I go clockwise or counterclockwise, should give me the exact same ratio. So for the first one, that would be pi/6. I would go ahead and just say pi/6. That was a weird 6, my apologies. So pi/6 plus 2 pi k is one of my solutions. It's actually 1/4 of my solutions, actually. Then I go to the next one. Well, the next one in the sequence, if I continue around, is over here in the second quadrant. That one is 5 pi/6. So everything starting at 5 pi/6 and going full rotations around, that also should be still a sine that's equal to positive 1/2. Then I move on to the other two angles that I notice. I have 7 pi/6. I don't know why I did another equal sign. It's just going to be a comma. So this would be 7 pi/6 plus 2 pi k. And then the last one is going to be 11 pi/6 down there in the fourth quadrant plus 2 pi k. Again, if I wanted to, I could answer this one. This one didn't technically force me to answer in radians. I just kind of made that decision, mainly because the other examples all were already talking radians, so why not just stick with that same thing? But I actually could have answered all of these based on how this was presented in degree format, so I could have said something like 30 degrees plus 360k, 150 degrees plus 360k, what would the next one be? 210 plus 360k, and then 330 plus 360k. But again, those numbers, in my opinion, are larger, and I don't really like writing those necessarily larger values. And more, I guess it's probably because I'm more accustomed to radians. But if the problem didn't technically tell you what to answer in, whether it said radians or degrees, you technically can do either. Just make sure you're consistent. Don't say something like pi/6 plus 360k, because now you're talking radians, but then adding degrees, that's not really the same unit. Now, you might have noticed that there would have been, for this specific example, an actual shortcut for our answers. Instead of having to write all 4 of these out, we actually could have done it in 2 statements, because after all, if we go with the pi/6 and the 7 pi/6, they actually are exactly 180 degrees away from each other, so I could have taken advantage of just starting at pi/6 and saying, let's just add half a rotation pi k, and technically that would just alternate back and forth between this angle here on the right. Let's see if I can differentiate this. So this one on the right, and then maybe do the one on the left, and it would just keep, every time I add half a rotation, bounce back and forth between those two angles. And then I would have to do another one over here starting at 5 pi/6 and then add pi k to it, and it would give me the other end, and again it would just be bouncing back and forth between the two. I'm not going to require you to ever have to like come up with all of the shortcut ones if they do exist. I think the safest route is just write down every angle that it happens to work at inside of one rotation, and then just consistently say plus 2 pi k. Answer keys, if you check them, sometimes might have the more condensed version. Just realize if it did say something different like plus pi k or plus pi halves k or something along those lines, that just means all of the angles maybe are exactly the same amount away from each other. So why not just take advantage of writing it as a little bit more of a shortcut. But for this one, I think, again, it's easier to think in terms of, let's just list all 4 of them out. I think that most you're going to have is 4, and then just say plus 2 pi k at the end of each one, and voila. We could just say all of that collectively, that's my answer, and move on, not worry about trying to come up with any sort of shortcut, if you will. Now, thus far, the three examples I've worked through have all been just single trig equations. I did mention at the very beginning that it can have certain times where maybe multiple trig functions or trig expressions get involved inside these equations. And ultimately what we'll need to do at that point is maybe try and find a way to simplify. So the skills that we built back in like 7.1 and 7.3 with the whole kind of replace parts of trig with maybe identities that are from our formula sheet to make things look a little bit nicer. Sometimes that's going to be our approach when it comes to how I actually would want to solve. Now, in other cases, maybe we might have some ratios that don't match things from the unit circle as nice as the other examples have as well. So I'll work through one where we need to bring a calculator into the problem to actually come up with what our solutions are, but still keep in mind if it gives us like a set restriction like 0 to 2 pi or 0 to 360, I don't really have to worry about anything special. I just go one rotation around unless there's a coefficient on the x. I might go multiple rotations around and realize I might divide back down into the first rotation. But I also potentially might have somewhere I have to do like all solutions, so introduce the plus 2 pi k or plus 360k depending on what type of angles or what type of measurements we'll be using for the angles. So the example 7 here that I'll eventually get to is one of those such examples where I would need to use a calculator to come up with my solution. So one such example of those types of problems that involve some form of simplifying or factoring is the one that you can see on the screen here. One thing that kind of is a dead giveaway is I have two parts or two terms that have cosines, so it for sure is going to involve some form of factoring to try and find a way to get them into a product and not have them completely separated. So that's going to be our approach. We're going to actually think of this more like it's a quadratic, and I hope that makes sense why. That I do have a power of 2, and I also have a power of 1 as well as a constant. So this is going to eventually, if I move these two terms over to the left, and ultimately how I would do that is I would add cosine of x for this part, and I would take away 1 for that. And that would now give me 2 cosine squared of x added with cosine of x, but then minus 1, and now being set equal to 0, which is, if you think back to quadratics, one of the better strategies to try in most cases is to try and get 0 on one side and then approach it as a let's hope that I can factor. So the way that we would factor something that has a coefficient that's not a 1, if you recall, is just multiply the a and c values. So 2 times negative 1 would give me negative 2. Think in terms of I need to multiply the negative 2 that adds to the middle coefficient, which technically you can picture there's like a 1 in front of that cosine. So that successful pair of numbers that satisfy those two things would be a 2 and a negative 1. And if it helps, you can kind of think of this just in quadratic form, so picture it like it's x's instead of cosines, and just say that maybe I have 2x squared and a negative 1 as like the first and last terms. Then the middle term I use the two numbers I just identified, so a 2x and a negative 1, or sorry, negative x in this bottom left. And now just think in terms of what would be on the outside. So it doesn't really matter if I start with a row or column, I'll just go with the first row. They both have a 2 and an x. So I know 2x would be on that left edge, and now it's just kind of fill in the pieces of the puzzle. So 2x times what would make 2x squared? Well, that means an x has to be up here on the top. X times what would make negative x in the bottom left? Well, that has to be a negative 1. Negative 1 times what would make negative 1? Well, that's got to be a positive 1. And then lastly, double check 2x times 1 does in fact make the 2x. That's the last box. However, again, as I mentioned, it's not technically x's, it's actually cosine of x's, so this would become one of the factors being 2 cosine of x minus 1. That would be using the left edge of this Punnett square, and then the next factor would be using the top, so that would just be a 1 cosine of x, then added with the 1 that I had. And notice I've now turned what was a sum and difference now into a product. Specifically, it's a product set equal to 0, so what I can now do is take advantage of if either of those factors was 0, the whole thing would be 0. So I'll set each of these now individually equal to 0 and solve just like we did with the first example of this video. So I would add 1 first. That gets me 2 cosine of x is equal to positive 1. Divide the 2 off. So I'm going to solve for this one, anything that makes cosine of x equal to 1/2, that's going to be a part of my solution set. So if I think of where is 1/2, I'll just use this space up here in the top right. 1/2 for an x value would be the ones closer to the y-axis in the first and fourth quadrants. So those two angles in this case, since it is degrees, are going to be 60 degrees And it does say only from 0 to 360, so I don't need to worry about plus 360k or anything weird like that, like the previous example. But it's going to be 60 degrees for the first one, and then the next one is 300 degrees in the fourth quadrant. Going on to the second one, I don't know why I didn't write the equal 0, but I am going to set it equal to 0 because that's the other factor. And do similar approach, just try and get cosine by itself. This one actually only requires one step, just subtract the 1 over, so I just need to figure out when is cosine equal to -1. Well, cosine is -1 on this actual x-axis, so that actually, if you think about it, is either 180 degrees or pi. So for this one, since it's a degree interval here, I'm going to make sure I answer in degrees, and so there are my 3 solutions inside of the 0 to 360 range. And I didn't have to go any further around, as you can see, because the x's that were inside were just 1 x's, so I only had to go 1 rotation around. Had those, for whatever reason, had like 2 x's or 3 x's or 4 x's on the inside, then at that point I would have worried about maybe going a second rotation or third rotation or fourth rotation around, and then knowing that I would have to potentially divide by whatever that number is to bring it back inside of the range. But again, this problem I didn't need to worry about it because the angles were just single x's, so it's just one time around, list out whatever solutions we got, stop when I get to 360, which I did, and so now I collect those up. There's my 3 solutions that happen to work. Try out another example, because I feel like the more you see, the easier it is to kind of recognize some patterns. Here, similarly, I've got multiple trig expressions. This time, though, I've got actually different kinds. I have cosines intermixed with tangents. What's nice is at least a couple of the terms have tangents, so similar to our last problem is I probably just want to get everything to one side. So if I just subtracted tangent of x, that would give me the ability to have 0 over there. I'd now have 2 cosine squared of x times tangent of x minus the tangent of x I'm moving over, and now equal to 0. So I do have 2 terms. Again, why I know it's 2 terms is there's only one addition or subtraction. So what I'm going to do is just factor out what they have in common. They both have tangent of x, so I can move that in front and write what's left. So from the first term, that would leave 2 cosine squared of x. And from the second term, since it technically is taking tangent of x out of itself, it does have to leave something there. In this case, it would leave a -1 because of the minus sign. And on the right side, it still is equal to 0. But now, because I've turned that into a product, I can do the same step as I did in the last example, just split it up into 2 expressions now, where tangent of x equals 0 is going to be some of my solutions, and then the other part, 2 cosine squared of x minus a 1 equaling 0 is my other list of solutions. So the first one, tangent of x equaling 0, that's already got my trig isolated, so tangent is 0 if you recall. I'm just going to draw another sketch up here in the top right. Tangent 0 at 0 and pi. In this case, notice it actually is switched back to radians, so I'm going to answer in radian form. So I know 2 of my solutions are going to be 0 and pi. 2 pi technically would be a solution, but notice it actually has a parenthesis next to 2 pi. So I don't include it, I just get as close to it as possible. So those are the only 2 that satisfy this first tangent of x equals 0. Now the other equation I would have to do a little bit more work with. I have to try and isolate it. So first add the 1 over. It gets me 2 cosine squared of x equaling 1. Now I divide the 2 off. So I've got cosine squared of x equaling 1/2. And then the last thing would be take a square root, and just like earlier, when I take a square root, I need to remember a plus or minus symbol. Here, what gets a little tricky is that plus or minus for the square root of 1 is going to stay 1, but the square root of 2 on the bottom, I can't really do anything with, so I will actually have to do a rationalized step of multiply by rad 2 on top and bottom, and notice we get a plus or minus square root of 2 over 2. So where is cosine equal to either positive or negative square root 2 over 2? Well, that actually should be all of the middle angles in all 4 quadrants, because I'm actually looking for not only the positive ones, which are in the first and fourth quadrant, but also the negative ones, which are in the second and third quadrant. So all 4 angles in the middle, which are all the pi fourths, are going to be a part of this solution set as well. So if we just start at the beginning, it would be pi fourths for the first one, 3 pi fourths next, 5 pi fourths after that, and 7 pi fourths to finish it up. So sorry, it kind of ran all together there, but that would be my list of, what do we got there? 6 angles total that technically would satisfy making this original expression equal to 0. Now if you wanted to try and check your work, again it would be double check the mode that your calculator is in, and basically you could go and plug all of these angles into the original expression just to make sure that it does truly match, or you could technically go with your factored version if you're confident that you factored it correctly, and just make sure that it gives you a value of 0 in the end. But that would be, again, just a way you could verify for yourself that your answers are good. It's not necessarily something that you have to do from time to time, but for those that just like to have that confidence of, I know these are correct because I checked it, that would be the way that you could go about doing it. Let's go ahead and try another example here where we've got to do some kind of prep work, if you will, before I can actually get to even trying to do a solution. Here the issue is I've got 3 different terms. They don't share anything in common, and I also have 2 different kinds of trig functions, so it's not as easy as the quadratic that I had earlier where everything was cosines. This is now kind of a mixture of 2, so what I would try and do initially is see if there's a way that I can either turn my tangents into secants or my secants into tangents. Really, I can't do much with just single power terms, or there's not as many options, but I can take advantage of this power of 2 does have something I can replace it with because of the Pythagorean identities. So tangent squared, if you recall, was the same as doing secant squared of x minus 1, and then basically from there I'm going to go ahead and just kind of keep everything else as is, and then hope that I can maybe turn this into a quadratic. So it does look like I do have a couple of like terms. I can actually combine the 2 negative ones and make that turn into secant squared of x plus secant of x, and then minus a 2 at the end, where I hope we can kind of see like this is somewhat fitting that same profile as earlier, where I could do the a times c strategy and what multiplies to b, but here it's just going to be what multiplies to negative 2 that adds to the 1. Because my coefficient in front's a 1, I can actually go straight to my sets of parentheses. So the pair of numbers that would satisfy the I want to multiply to negative 2 but add to 1 would be a negative 1 with a positive 2, and instead of it being x's, this time it's actually just secant of x's. And again, that's still equal to 0 on the right side. It was just a matter of I didn't necessarily have to go the full Punnett square route and factor things out because that coefficient in front was a nice 1, so the factoring of that quadratic was a little bit easier than the earlier example. From here, though, it's going to be the same general thing that we've been doing. We'll go ahead and try and get each of these isolated and set equal to 0 on their own. So that would now turn into secant of x equaling positive 1 if I add the 1 over. Sorry, I didn't show that step, but I assume we probably could have figured that out. And now it would just be, okay, if secant of x is equal to 1, that's really when is cosine of x equal to its reciprocal 1. Well, that's something I can reference on the unit circle. Cosine is equal to 1 over here at 0 and 2 pi and 4 pi and so on and so forth. So that's where the instructions here at the beginning, it's just 0 to 2 pi. So ultimately for this one, it's just going to be one solution of it's going to be 0. The second one, on the other hand, is going to be, let's go ahead and set secant of x plus 2 equal to 0. Move the 2 over, so I get secant of x equals to negative 2. Secant of x is the same as 1 over cosine, so if I switch the right side to be its reciprocal, if secant is negative 2, cosine must be negative 1/2. And now reference when is cosine equal to negative 1/2. I feel like we've had that one earlier in the video, but it would be these two angles in the second and fourth quadrants. And for that list here, that would just add on the couple of pi thirds that we got right there. So this is going to be 2 pi thirds from the second quadrant and 4 pi thirds from the third quadrant. And I knew those ones were the thirds because they were the ones closer to the y-axis. It's always the ones closer to the x-axis that would be the sixth. So it would be essentially inside of the 0 to 2 pi range. It would be that list of 3 angles in radian format specifically that would actually satisfy the original. The plugging into this one on the calculator would be a little bit trickier just because we don't necessarily all have a secant button that we could use. So at this point it would be maybe I could type it in as 1 divided by cosine of the angle if I wanted to double check. But so far so good, I hope. With this one, I don't see any glaring mistakes that we have in the problem itself. So I feel like those ones should, in good conscience here, work out when I do plug it in. So I would go ahead and feel good about moving on. All right, we'll go ahead and move on to our last example. As mentioned earlier, this is the one where it's actually going to be, the only way I can solve it is if I had a calculator nearby. So this is, again, something to kind of just show, like, how would we go through this process if it was maybe not ratios from the unit circle, or let's say maybe it just wasn't a very nice thing to factor. So this is one of actually both of those examples. I can't really factor this very nice because if I try doing the 10 times -7 strategy, there really isn't anything that multiplies to this -70 that would add to the -12 that's in the middle. So trying to factor actually would not work even though this is in a quadratic form. Now what's nice is because it's in a quadratic form, we can actually utilize the quadratic formula, which normally would start with x equals, so quadratic formula, if I write it up here, would be x equals -b plus or minus the square root of b squared minus 4ac, and then all of that's over a 2a. Except in this case, it's not just x's that are there, it actually is a sine of x. So how this would work with trig getting involved in this quadratic form is I would actually say sine of x is equivalent to, and start plugging in the values from the quadratic in place of their a's, b's, and c's in the formula itself. So -b would in this case be -12, so that would be +12. Plus or minus the square root of -b squared, or sorry, -12 squared, which would be 144, minus the 4 times 10 times the -7 for the a and the c, all over twice a, so 2 times 10. And at this point, I feel like we could probably just try and simplify this utilizing a calculator. So let's bring one up. I got 144 minus 4 times 10 times -7. So that's really going to switch to addition, but let's just type it in. 144 minus 4 times 10 times -7, and in fact it gives me 424. And so let's go ahead and go back here and just say that this is the same as 12 plus or minus the square root of 424 all over twice 10, so over a 20. Now that 424, I'm going to just do a little bit of simplifying here over off to the side. I feel like that's probably a radical we can simplify a little bit, so I'm just going to take out as many 2's as I can. So half of that would take me down to 212. Half of that takes me down to, what is that, 106. And then 106 would be a 2 with a 53. So it looks like I just get a single pair of 2's that I could factor out, and then I'll probably just turn right back into a 106. So if I did that, I've got now 12 plus or minus the 2 that was able to pair up times the square root of 106. That's 16, but 106, there we go, over 20. And now all the numbers on the outside, the 12, the 2, and the 20, are all divisible by 2. So I'll go ahead and just divide them all by 2. 12 divided by 2 is 6, plus or minus the square root of 106, because the 2 would turn into 1, and now all over 10. So ultimately my equation now is when is sine of x equal to that, and I want to solve for when that happens inside of the 0 to 360. So in interest of space here, I'm going to go ahead and just get rid of that factor tree over on the right and bring the calculator in. Ultimately, I'll need to figure out what are these 2 decimals that I get. And if we think about it, since it has positive signs and negative signs, that's going to be, if we think about it, 1 in each quadrant. So I'll just need to figure out kind of what happens when it's a positive. That should give me what would happen in the first and second quadrants, because sine is the y value. And then what happens when it's negative? Well, that would be what happens in the third and fourth quadrants. Then we'll just find the reference angle on the unit circle and then use that to our, or sorry, not unit circle, but on the calculator, and use that to our advantage to be able to solve for all 4 angles that happen to exist inside of this 0 to 360. So first off, what I need to make sure I do, I'll go ahead and clear out what's there, is just double check we're in degrees, which I am. But again, you would just go to mode, make sure that degree is highlighted if you weren't in degree mode. And back here, I'm going to go ahead and just figure out what is the value of each of those fractions. So my fraction here, if I bring up the template, alpha y equals, first option was, in front I had 6 plus the square root of 106, then all over 10. That gives me this specific decimal. And ultimately what I would do from there is just try and figure out what is the inverse sign of that. So if I did the inverse sign of that answer and pressed enter, notice it actually gives me a domain error, meaning that that actually is not a ratio I'm going to have to worry about dealing with. So there are no solutions for that first part. So that takes what I thought was going to be 2 solutions and turns it into, or sorry, 4 solutions, and turns it into there's probably only going to be 2 solutions. So let's go ahead and go back up and highlight this, but then this time let's switch it to a minus sign. If I can get back to that minus, there we go. So switch my plus to a minus, press enter, see what that decimal is, and try to do the inverse sign of that answer. I get negative 25 degrees and about, let's go with negative 25.44 if I round that. So let's bring this back up. My angle so far that it gave me for the x, right, when I used the plus, I didn't get any solution because that actually was outside of the range for inverse sign, if we think back to what that would have been. But the other one I got was negative 25. Let's bring that up again, negative 25.44. So if I think about where that would be on my unit circle, if I were to draw it, it would be negative 25 degrees down this direction. And I would have another one that should be the same y value, right? If I think of the endpoints as the y values, where this angle here also would be a 25.44, at least as far as the amount is concerned. Now, even though the answer here came back negative on the calculator, we hopefully recognize that the answers it actually wants are in between 0 and 360. So what I actually need to picture is like how much is this angle here, as well as how much is this angle that goes all the way around to here. So the first one there is pretty simple, I would think. If I know that the 180 is here, it's just going to be add the extra 25.44 to it. So if I just did 180 plus the 25.44 I've just found, one of my solutions is going to be the 205.44. So that's going to be one of my final solutions here. So x equals, let's change my color, x equals the 205.44. There's my first solution. And then the second one would be essentially just go 360 more than the angle that I had right here. So if I just did plus 360, that should get me my second answer. So if I go back to 360 and add it with the negative point, but negative 25.44, that gets me my last answer of 334.56. And each of those are in degrees, so make sure that we have our degree marking, and that gets us our final solutions for this specific problem. So notice when it gets ugly, we still can use a calculator to go through and do it. We on occasion, as we saw here with this example, when we use the plus sign, we might get some values that when I try and cancel the trig function itself, that might fall outside of its allowed range, or domain rather, where it would give me an error on the calculator. That basically just means for that portion of this quadratic, it actually has ratios that wouldn't exist for the sign, so we would just move on to what are the other options. Well, that's when I switched to the minus, figured out that decimal, did the inverse sign or arc sign of that actually gave me a value, and then used that as a reference. So notice again, our reference over here was the 25 degrees below the positive side of the x-axis and the 25 degrees more than the negative side of the x-axis. So all I had to do was add 180 to the 25, or sorry, that actually would have been, for this one, 180 plus the 25.44. That's explaining where the first angle came from, and then the other one is, I know it's the 25 degrees less than 360, or I could have just said, well, from the negative 25 degrees, I just go one full time around. That gets me the same spot. So adding 360 was really more the approach I had with that one. But anyway, as we work through more and more examples like this in the homework or in class, we can work through other examples as well. If you have questions, please let me know, and I can try my best to make it make sense. Ultimately, I hope you're starting to see some of the patterns where the general idea is, if I see the ability to factor things, try and factor right off the bat. If you notice there's only one trig equation, just try and, or sorry, not trig equation, but trig expression, just try and get it isolated and try and solve, and hope that you match some ratios from the unit circle. If you have some ratios that maybe don't come from the unit circle, such as this example, then we know we'd have to bring a calculator in and just utilize reference angles for the correct quadrants. I knew that sine was going to come back as a negative value at negative 25 degrees, which is why I knew it was going to be in the third and fourth quadrants, or the below half of the unit circle, which is why I knew I could come up with those two angles just by either adding to 180 or taking away from 360, or even just adding a full 360. Last one just kind of works both ways, but again, it gets a little bit trickier when it's not angles that we can perfectly see on the unit circle, but there still is a way to account for it. I'm not really going to push the envelope that much in this specific class and do anything like this last example. I just wanted to at least have one where you could kind of see, like, okay, I can somewhat understand like where those values are coming from and why we would do those things, but I'm more going to stick with, as far as like my assessments, they're going to be more related to things that are from the unit circle, to try and hopefully keep numbers in at least a nice and somewhat simple way of being able to come up with our values. And also our answers would make a lot more sense as far as the numbers that we're writing down, because they're familiar values. But anyway, hopefully this video hasn't taken up too much of your time. Hopefully most of it has been helpful, but as always, like I mentioned there just a second ago, if you have questions, just come find me. We'll get it figured out, work through some more examples as need, and hopefully we can get it all figured out. But as always, I appreciate you taking the time to watch the video, and we'll catch you next time.